Welcome to Module 3, Lesson 7. We are going over hyperbolas. So to prepare for this lesson, you need to be familiar with ellipse. We're about to start this lesson by comparing your ellipse formula to your hyperbola, and you're going to see a lot of similarities. So if you haven't watched ellipse, you need to go back to last lesson to watch ellipse, and then we also need to complete the square. We will need that for every conic section. So make sure you have watched this additional lesson on page 223 or whatever page it is now, in the extra parts of your spiral to make sure you are up to date on that. We have several learning objectives. We need to be able to analyze and graph hyperbolas with the center at the origin. We need to be able to find asymptotes of a hyperbola. And so actually that's also some of the preparing for this lesson. You need to be familiar with asymptotes. So I will add that to this section. And that's in your rational functions, which is lessons 1 and 2 of this unit or this module. You need to be able to analyze and graph hyperbolas that are centered at HK. So once we have shifted from the origin. And then as always, in all of these conic sections, you need to be able to know the general form of an equation of the conic section, specifically understanding how the constants of the equation relate to the graph. You have already used this QR code. But as a reminder, you can pause and rewind this video as often as you need, so this lecture is at your own pace. And then you need to look at your course schedule to see when this homework is due. So we are going to go ahead in this intro video, get into our lesson. But before we do, I want to start off by again comparing our equations like we did last time. So here are our formulas for ellipse and our formulas for hyperbola. Please pause this video and find all the similarities and differences of these two equations. Okay, I hope you had time to pause. As you can see, every numerator here still has this x minus h squared and y minus k squared. Over here, it is switched though. So those are switching places when it is parallel to the y. All of these equations equal 1, so that's another similarity, and they all divide by a squared and b squared, but as you know, a squared and b squared change for the ellipse, and so we could tell whichever one was a by whichever was the larger number. So if our larger number was under the x, it was parallel to the x. If our larger number, a squared, was under the y, it was parallel to the y. When you go to hyperbola, since my x minus h quantity squared can switch places, if you notice these denominators, which really bothers me that the font is off, but you get the point, the a squared and b squared stay the same. A squared here always comes first. That's going to be kind of the biggest change when we have these. And so if you look at your formula sheet, which is in the extras as well, I make that very clear. When you have an ellipse, I make a note here that your a squared is always the largest. And then when you look at your hyperbola, I make a note that your a squared always comes first. So it doesn't change. What changes is that x and y. So that's kind of the biggest difference. Well, the biggest difference that's going to trick us. The actual biggest difference is that what makes an ellipse different from a hyperbola is your ellipse has a plus in the middle. Same with your circle. Hyperbola now is subtracting. And so typically we always put the positive coefficient first, but that isn't always the case. But the big thing is they have opposite signs, right? You have a positive x and a negative y. Here you have a positive y and a negative x. So they have opposite signs from each other. So let's get into our notes now that we've kind of compared our formulas. And here's our definition of a hyperbola. A hyperbola is the collection of all points in a plane. This time, the difference of whose distances from two fixed points called the foci is a constant. So this one is different. So this is actually the exact same definition of ellipse, except they had sum and now it is difference. And so what that constant is it is again the same as it was before as 2a, but now that we're subtracting, it could be plus or minus 2a. And so they don't put this diagram on this picture, but let's do a highlighter here. If they put some random point on my hyperbola, which is these two blue lines, put some random point, the distance from that point to focus 1 and the distance from that point to focus 2 will be a constant number no matter where you put that point. So you can see here, if you subtract this distance from this one, you're going to get a negative 2a. But if you subtract this distance from this one, you get a positive 2a. So it just matters the order that you subtract, but that number value will be the same. Another way to write that instead of plus or minus 2a is the absolute value of 2a. So when we get into graphing, we want to be able to graph this. And again, that all of that red in here, and I should have explained that with the ellipse, because the ellipse also had your foci in red. That's not really part of your graph, right? So all of this bit that's in red, and actually even including the center, is not part of your graph. The graph are just these two blue lines. So when we graph, we need to plot 5 points. We will plot the center, and I should have done this with the ellipse too, but we're going to plot the center, and I'm going to put the center in red because again, it's not actually part of the shape of this graph. Here we have 2 vertices, and I don't say major vertices here. We have just one set of vertices, and so that are these V1 and V2 right here. We're going to have 2 foci, which I'm also going to put in red because these 2 foci aren't technically part of my graph, but they're part of that definition. So we're going to graph it. And more specifically, my math lab's going to ask you questions involving it. And then the last thing that we need to be able to plot, it says plus the 2 asymptote lines. So they're not drawn in here, and this is going to get a little crazy looking. But we have 2 oblique asymptotes here. And if I go through the center, there's one asymptote. And here is the other one. We're going to have 2 asymptote lines going through. And this is what's going to kind of guide my shape of my graph and tell me how wide these 2 hyperbolas are. Or if this line was more this way, then we'd have, you know, a not as wide, but a more narrow hyperbola. So we need 5 points plus the 2 asymptote lines. So when we go to a graph and we just looked at those formulas, we're still having A, B, and then my foci are still going to be my C. So let's talk about what A, B, and C represent in that graph. A is still the distance from the center to your vertices, but this time we don't have major vertices. So I'm going to put to the only 2 vertices. And I want to make that very clear that we don't have 4 vertices anymore like we did with hyperbola, or goodness, with ellipse. We had 2 major and 2 minor. We just have 2 vertices that are represented by A. Now this one's not going to make sense until we get into an example, but B is going to be the distance between the center, from the center, to help make what we're going to call the box. And let me actually put the box in red because we're going to put the box in red. So the box. And then lastly, C is still the distance from the center to your foci, which will also be in red. Okay, so When you start next video, we will start graphing these and applying all of this information and these points and stuff.